All right, today we're going to do something really cool. We're going to build a learning machine, right, from the ground up. We're talking about going from just a huge pile of messy, raw data all the way to a smart model that can actually predict things. So the big question is, where do you even start?
It really all boils down to this one question. And hey, forget about the sci-fi robots for a second. At its heart, machine learning is really just a process of teaching. But instead of textbooks and classrooms, our learning material is data. So how does that actually work?
So here's the roadmap for our journey. It's got 5 main stops. First, we'll start with the most basic ingredient, the raw material, the data. Then we'll sketch out a blueprint for our model. After that, it's time to send it to school. That's the training process, which is, of course, followed by a final exam to see what it's learned. And finally, we'll look at the secret sauce for taking a model from just pretty good to truly great.
Okay, so first things first, it is all about the data. I mean, you could have the most brilliant, sophisticated algorithm in the world, right? But it's totally useless without the right fuel. And in machine learning, that fuel is good, clean data.
And getting that fuel ready, well, it's basically a 3-step process. First, we've got to find and grab the exact data we need, that's querying. Then we have to clean it all up, which we call preprocessing. And finally, we standardize it just to make sure everything is being measured on a level playing field. Think about that first step, querying. It's literally like going data shopping. You've got this massive warehouse full of data, and your job is to go in and find only the specific pieces, the exact ingredients, that are relevant to the problem you're trying to solve. Let me tell you a secret that every single data scientist knows deep down. Raw data is a mess, a total mess. It's usually full of mistakes, missing information, weird formats, you name it. Pre-processing is that absolutely critical cleanup job. It's like washing and chopping your vegetables before you even think about cooking. You have to ensure the model learns from quality ingredients. Okay, so imagine you're looking at data about houses. You've got the price in hundreds of thousands of dollars, and then you've got the size in square feet. Those numbers are on completely different planets. An algorithm might get confused and think price is way more important just because the number is bigger. Standardization fixes that. It puts everything on the same scale, so we're finally comparing apples to apples. All right, so our data is squeaky clean and all on the same scale. Now we can get to the fun part, stage 2. This is where we design the blueprint for our model. It's where we decide what kind of problem we're actually going to teach this machine to solve. The most common way to do this is something called supervised learning. And honestly, it works just like using flashcards to study for a test. We show the model an input, let's say a photo of a dog, and we give it the correct output, the label, dog. You do this thousands or even millions of times, and eventually it starts to learn the patterns. Now, within supervised learning, you're usually doing one of 2 big jobs. First, there's classification, where you're trying to put something into a category. You're asking, is this email spam or not spam? Then there's regression, where you're trying to predict a specific number, like, what's the price of this house going to be? The real difference is the kind of question you're asking. Are you sorting things into buckets, or are you trying to predict an exact number? Okay, so we've got our data. We've got our blueprint. Now we get to the heart of it all, the training process. This is where the magic really happens. This is where the learning actually begins. You can think of training as this giant game of getting warmer, getting colder. The model makes a guess, we show it the right answer, and it sees how far off it was. Then it tweaks its own internal knobs and dials, we call them parameters, just a little bit to try and make a better guess the next time. And it does this over and over millions of times, slowly getting better and better. But, and this is a big but, training isn't so simple. There's this classic trap, this fundamental problem called the Bias-Variance Tradeoff. You have to imagine it like walking a tightrope. On one side, you risk building a model that's way too simple to be useful. But on the other, you risk building one that's so complicated it just ends up memorizing random noise. So on one side of that tightrope, you've got what's called high bias or underfitting. This is like a student who barely studied for the test. The model is just too simple. It hasn't grasped the core concepts, so it misses all the important patterns. Its predictions are just going to be wrong pretty much all the time. And then, on the other side, you have the complete opposite problem, high variance or overfitting. This is the student who didn't learn the material, they just memorized the textbook word for word, including all the typos. The model looks perfect on the data it's already seen, but the second you show it a new problem, it completely falls apart because it learned the noise, not the actual lesson. So we've trained our model. We've walked that tightrope very carefully. But how do we really know if it learned anything? I mean, for real. Well, it's time for the final exam. We're going to test it on data it has never, ever seen before. This whole process is called model validation, and its entire job, its only job really, is to see if the model can generalize. Can it take what it learned from its study materials and apply that knowledge successfully to new, unfamiliar problems? That is the ultimate test of learning versus just memorizing. Now, there are a couple main ways to run this test. First is the holdout method. Think of it as the quick and dirty approach. You split your data once, train on one part, test on the other. It's fast, but your score could be a bit random based on that one split. Then you have k-fold cross-validation. This is the more, let's say, by-the-book rigorous professor. You split the data into multiple sections, or folds, and test on each one, then average the scores. It takes more work, but the final grade you get is much, much more reliable.
So how do we actually grade this exam? What's a score? Well, we use specific scores called evaluation metrics. The most famous one is accuracy. It's simple. What percentage of the time did the model get the right answer? These metrics give us a hard number, a real grade, so we can judge exactly how well our model performed.
Okay, we've built a model, it works, it gets a passing grade. But in the world of machine learning, let's be honest, good enough is rarely good enough. So how do we push it? How do we go from good to truly great and build a world-class model? This is where one of the coolest, most powerful techniques comes in, Ensemble Methods. The idea is actually super simple, and it's based on the wisdom of the crowd. Instead of trusting just one expert model, you train a whole team of different models and then let them vote on the final answer. It turns out that this team approach usually crushes the performance of any single model working alone. And a rockstar example of this is something called XGBoost. Seriously, this thing dominates machine learning competitions. The way it works is just brilliant. It builds models one after another. The second model's main job is to fix the mistakes the first one made. The third model's job is to fix the mistakes the second one made. And on and on. It's this chain of continuous improvement that makes it so incredibly powerful. But after all this data cleaning, training, and testing, we have to step back and think about the most important thing of all, model yield. I mean, think about it. What good is a model with 99% accuracy if it's too slow to be useful, or cost a fortune to run in the real world? Yield is the true measure of a model's success. It's that perfect balance between accuracy and just plain real-world usefulness. And that, right there, brings us full circle to the single most important question you can ever ask. It's so easy to get lost in all the cool tech and the numbers, but we can't forget the goal. Accuracy is just a number. Yield is about creating real value. So the final question is always, what real-world problem are you actually solving?